Okay, so let's talk about what is a generator. So earlier in this course, we talked a little bit about motors, right? When we were working with servo motors and the Bobot, we talked a little bit about what motors were and how they worked. So what we said is that a motor was essentially an electromagnet on the outside of a sort of a metallic housing, and then there was a permanent magnet in the middle of this housing that was connected to a shaft, right? And this permanent magnet spun around and caused the shaft to turn, right? So the permanent magnet always had a north pole and a south pole, like that, and then we turned the electromagnets on and off in order to make this permanent magnet turn around, right? So we put electricity into the motor and we got rotation out. Well, the funny thing is that if you take a motor and you turn the shaft, even when the electromagnets are not connected to any power source, you will get electricity coming out of the wires for the motor. Okay? So it sort of works both ways. If you put electricity into a motor, you get rotation out. If you put rotation into a motor, you get electricity out. So it does go both ways. And that's really all that a generator is. It's basically a really big motor, and you force the shaft to turn, and that creates electricity. Okay? So that's really all that it is. Now, the more magnetic field you have in the middle, basically the stronger this permanent magnet is, the harder it is to turn the shaft, but the more electricity you get out. So if you want to create a whole lot of electricity, you want to have a really, really powerful, strong magnet in the middle. Okay? And it turns out that it's hard to find real permanent magnets that are that strong. So instead of using a permanent magnet, what they do is they actually make this thing in the middle an electromagnet as well. Okay? So they take wires and wrap it around this middle core, and then they put a lot of electricity through these wires, always in the same direction, so that the magnet is always facing, the same way, but they put a lot of electricity through there, so it creates a very, very strong field in this magnet. Okay, so they get a whole lot of magnetic field out of this permanent magnet in the middle. And this electricity in the middle is always going in the same direction. So we call that DC electricity, direct current. The voltage never changes. So it takes this DC energy into a generator to actually create electricity. So you're using electricity and a lot of force turning this shaft to create more electricity. Let's talk about the electricity that comes out. If you were to look at a graph and look at the voltage that was coming out, what you would see is that as this north pole swings past this top part of the magnet, swings past this top coil, you might get a positive voltage coming out. But then, as the north pole moves away, the voltage goes down. And then, as the north pole moves past this bottom coil, the voltage goes in the opposite direction. So it looks like this. And then as it moves away from the bottom, the voltage goes away. And then as the north pole swings past the top coil again, the voltage goes up and gets positive. So the voltage coming out of our generator looks something like this. We call this AC electricity, alternating current, because the voltage alternates between positive and negative values. Okay. So this type of generator creates AC electricity. So we put in DC electricity to create this magnetic field, and we put in a lot of force to turn the shaft, and we get out AC electricity. Yeah?
And AC is the type that homes use?
That's right.
Yeah.
Yeah. So if you were to attach an oscilloscope to the wall outlet, please don't do this, but if you were to do that, then you would see this type of signal. Okay? We'll actually do a lab later on where we view the electricity in the wall, but we're going to use a device between the wall and our oscilloscope to make it lower voltage so that it's not dangerous. If you were to plug the oscilloscope straight into the wall, you could easily get shocked. So that's a dangerous thing, and you should not do that. But we will do that safely later in the course. Okay. So when you are talking about the AC electricity in the wall, that has a particular voltage. That's at 120 volts, and that's RMS voltage. Okay, we'll talk about that later in the course also, but it's 120 volts, and it has a frequency also. So the frequency is 60 hertz. That's 60 cycles per second. So that means that this sine wave pattern repeats 60 times every second. Okay? And this sine wave pattern is being created by our generator. So that means that the generator has to be moving at a very specific rate. Okay? If the generator was moving too fast, then the electricity in the wall would be going too fast. If the generator slowed down, then the frequency of our electricity in the wall would slow down. So the speed of the generator is directly related to and actually creates the frequency of the electricity in the wall. Okay? So it's important to keep the generator moving at exactly the right speed, because we don't want the frequency of the wall to change. So nowadays, it's fairly easy to do that. You know, you have computers that can do that, right? And then special sensors, and it's probably done all electronically, right? But remember, this was created back in the 1800s. So they didn't have a lot of computers back then. So they needed a different way to keep this generator turning at exactly the right speed. So they actually used a really clever device called a flyball governor. Has anybody heard of one of these? So this is one of those, you know, weird pieces of science equipment that shows up a lot in movies and things and looks really cool, but nobody really knows what it does. Okay? So it's one of these things where there's a vertical shaft, and there are these two sets of arms, basically, that go out like this, and there are these big metal balls on the end of the arms. Okay, so they rotate around like this. You might have seen them on top of trains or things like that. And this is actually a real piece of equipment, and you can see one of these at the powerhouse when we go. So the way that these work is that as the shaft starts to turn faster, you get more centrifugal force. So the arms get pulled out. Okay, so if it was turning really fast, the arms might get pulled out, you know, and be somewhere like this. Okay. Whereas if it were turning more slowly, there would be less centrifugal force, so the arms might be lower. They might be more down here. And what happens is that there's a sort of a collar that's attached to the bottom of these arms. And as the balls go farther out, the collar moves up, and as there's less force, the collar moves down. And this collar regulates and controls the flow of water in this case. Okay? So, and this whole thing acts to keep the generator going at the same speed. So basically, what happens is that the speed of rotation of this shaft is connected to the speed of rotation of the generator. If the generator starts moving too fast, the arms get pulled out, the collar gets lifted up, and that restricts the flow of water that's coming to the generator. Okay, that's connected to like a gate that controls the amount of water. So as the collar goes up, it reduces the flow of water to the generator. So that means that there's less force acting on the generator, it slows down a little bit, and then the arms move back in, and the collar slides down a little bit. Yeah?
What's the name again?
It's called a flyball governor. Conversely, if the generator starts to slow down, maybe the water pressure reduces, or people are using more electricity, so it's harder to turn the thing. If it slows down, the arms sort of relax a little bit, the collar gets moved down, and that allows more water to come in and forces the generator to speed back up again. Okay, so this is called feedback control. Basically, this device measures the output and then controls the input to the generator based on what the generator is doing. So feedback control is used all over the place now, but this is one of the very first devices that actually implemented a feedback control system. Okay? So these are really cool. You'll get to see one on Thursday, and I studied feedback control in school, so it's sort of near and dear to my heart. So, any questions about that? Okay. So that's how the power plant is able to keep the generator moving at the correct speed all the time.
So that means frequency, right?
Yeah.
So what controls the voltage?
Right. So, well, the amount of electricity going into this magnet here, this interior electromagnet, determines the strength of the magnetic field, and that will create the, or that'll determine the amount of voltage that you have. Again, they want to keep that voltage constant as well, because you don't want the electricity in your home to be changing voltage levels. So they want to keep that as constant as possible. So, any questions about that? Okay.
160 and 120. So just an
Yeah, somebody just decided that that was a good idea. That's not the way that it is all across the world. In other countries, sometimes it's 50 hertz. Certain countries have 240 volts instead of 120. So it just depends. That was just somebody's idea. that became the standard. The same goes for AC electricity, right? Why AC and not DC? Well, we kind of take it for granted now that it's AC because that's what everybody uses. But when electricity was first being implemented on wide-scale grids, there was actually a big debate about whether it should be AC or DC. So Nikola Tesla and Edison, yes, thank you. Thomas Edison were two big inventors, and they had different ideas. One of them thought that AC would be better, and the other one thought that DC would be better. And they had a giant war over this, corporate war. It was sort of like when, we were talking about whether it should be Blu-ray or HD DVD, right? There were two competing standards, and both companies stood to gain tremendous amounts of money if their standard won out. So there was a big debate, and in the end, everyone settled on AC, but it didn't have to be that way. That's just the way it came out. Now, there is a little bit of an extra wrinkle here. So far, we just see one signal coming out of our generator. But real power generators actually have 3 sets of coils. So they have another coil that is sort of like this, and here. And then they have a third set of coils, which are over here. And then the other coil would be right there. I'm not going to draw over my graph. So they actually have these 3 sets of coils. And so what happens is that, first of all, this north pole of the magnet goes by the first set of coils, and you get the first positive voltage. But then a moment later, it swings past the red coils there. So there's a little bit of a delay between the peak voltage for the black set of coils and the peak voltage for the red set of coils. So you get something kind of like that. And then it's another moment before the north pole swings past the green set of coils. So there's another delay between the peak of the red and the peak of the green. So you get voltages that look something like this. So each one of these signals is a little bit offset from the others. And the amount that the signals are offset is called the phase. Okay? So if the signal starts right at time 0, then we say that that's no offset, or a phase of 0. If it starts a little bit later, then it has a phase offset. So we call this 3-phase electricity. And there are 360 degrees in a complete rotation, and there are 3 sets of coils, so each coil is evenly spaced around the circle, so each coil is 120 degrees apart. So we say that there's 120 degrees between each phase. So if you've seen big power lines, you've probably seen that they have 3 wires on them usually. Well, each wire is for one phase. Okay, so they're distributing the three-phase electricity from the power plant, and each phase is on its own wire. Okay. Questions about that? Okay, so that's a little bit about power generation. We talked about what a generator is. We talked about how they work. We talked about the electromagnetic core. So now you know why it takes DC electricity in order to make AC electricity, right? We talked about the fact that it runs at 60 hertz, and we said a little bit about three-phase electricity.
In the house, you have only the dryer that uses three-phase, right?
Well, so that's a good question. Basically, why do we have three-phase and where is it used? It's actually not really used in houses mostly. It's used in industrial automation type settings. So big machines like mills and lathes and things like that will often use three-phase electricity. But in the house, it's typically single-phase. Now, you're right. So in the house, we use 120 volts for most things, but certain appliances like dryers, washers, stoves need more voltage. So they use 240 volts, but it's still single phase. And we'll talk a little bit more about that in just a minute.
So no phases at all.
Just one phase. So basically each home will get, one of these, the electricity from one of these wires. Okay? Okay, so let's talk a little bit about power distribution. We've talked about how we make the power, but now we need to understand how it gets from the power station out to other buildings that are going to actually use it. So what happens is that the power station is here, and it creates this three-phase electricity. And what it does is that it makes the electricity at very, very high voltages. And then it actually uses transformers to get the voltage even higher. So if you guys, we haven't talked about transformers yet, right? So let's talk a little bit about transformers. A transformer is a piece of equipment that takes AC electricity and changes the voltage. So it can take a low voltage and make it into a high voltage, or it can take a high voltage and make it into a low voltage. And the way that this works is that really a transformer is just two coils of wire that are really close to each other. Oftentimes these coils of wire are wrapped around iron bars or things like that. But essentially they're just coils of wire that are very close to each other. And the principle for transformers is really very similar to the principle that happens inside motors or generators. Okay? So we saw that when we were talking about generators, what was happening is that we were moving a magnet near a coil of wire. And that moving magnetic field created electricity in that coil of wire. So a changing magnetic field near a coil of wire creates electricity in that coil of wire. Well, what happens with transformers is that they have an input side and an output side, and you put AC electricity into the input side. So you've got electricity going through a coil of wire. Now what happens what do you make if you put electricity through a coil of wire? That's an electromagnet, right? So you put electricity through this coil of wire in one direction, you make an electromagnet in one direction. Say the North Pole is down here and the South Pole is up here. Well, then the electricity stops flowing in that direction and it starts flowing the other way because it's AC, right? So now the North Pole is up at the top and the South Pole is down at the bottom. So what you have is you have a changing magnetic field. It's always going north on the top, and then north on the bottom, and then north on the top. So you have this changing magnetic field right next to a coil of wire. And we know from the generator that when you have a changing magnetic field next to a coil of wire, you create electricity in that coil of wire. So that's what happens over here too. So basically, you put AC electricity in, and you get AC electricity out. Now I said that the main purpose of the transformer is to change the voltage, right? Either from a low voltage to high or high to low. So the thing that determines how much voltage you get out is called the turns ratio. It's basically how many turns you have on the output and how many turns you have on the input. So imagine that you have 100 turns on the input and you have 200 turns on the output. This is called a step-up transformer, and the voltage out is twice as much as the voltage going in. So you put in 5 volts, you get out 10 volts. Okay? So it's the number of turns, the turns ratio, that determines how much voltage you get out. Yeah?
Are they in phase?
Well, yeah, so on transformers there's usually a little dot up here and a dot over there, and the sides with the dots are in phase. So, so when the voltage goes up here, the voltage goes up on that side. Sometimes the dots are like this. So then when the voltage goes up there, the voltage goes up there. So it just depends on the transformer. So you can affect the voltage, right? You can get out more voltage than you put in. So do you guys think that this means that we could just hook a bunch of these together and power the whole city from a little battery? If we put in 9 volts, we could get out 1,000 volts, right? Probably not. There's no free lunch. What happens is that the power out is the same as the power going in. Okay, so you know that power is voltage times current. So that means that if you get out more voltage than you put in, you have to get out less current than you put in. Okay, so as the voltage goes up, the current goes down. So, but the power stays the same between the output and the input. Yeah?
So do people put like transformers in like series to increase current?
No, it wouldn't really increase the current, right? Because if you, so you're talking about getting more voltage out?
Well, you said that when you get more like volts, but the current decreases.
Right.
So if you had multiple transformers, could you increase the current but still have the same amount of that like increase of voltage?
No, the power out is always the same as the power in. So anytime you bump up the power, the current goes down. So even if you did it several times, you could increase the voltage more and more each time, but you would be decreasing the current more and more each time. Now the opposite is true also. If you have a transformer with fewer turns on the output, then you get less voltage out, but you do get more current out. So if you wanted to have more current, you could use something called a step-down transformer, which decreases the voltage, but then increases the current. Okay. And sometimes people do this tricky sort of modification to the transformer where they attach a wire right in the middle of this output coil. So this wire, when you have a transformer with this type of wire, this wire is called a center tap. So what happens is that if you have a total of 10 volts coming out, then you have 5 volts from the top to the center tap, and then another 5 volts from the center tap to the bottom. So the center tap splits the voltage. Okay. And this goes back to your question about the voltage in the house and the larger appliances and things like that. So what happens is that at a house, you have a power pole, right, with 3 wires attached to it. And then when you get to a house, what happens is that there's a sort of a big can-looking thing way up on the top of this power pole. So it's usually attached to the pole kind of like this. You guys may have seen these before, and it's got these 2 little funny antenna things sticking off the top. And they're usually attached to the 2 of the wires like this. And then coming out, you have 3 separate wires that go down to the house. So what's happening is that this is actually a transformer. Okay, so these 2 wires going in are providing the AC electricity in, and then there is a center tapped transformer in there. And it's stepping the voltage down to 240 volts out. The voltage on these wires is very high, but the transformer brings it down so that there's 240 volts between the outside 2 pairs. So that means that there's 120 volts from the outside to the middle, and then 120 volts from the middle to the other side. Okay? And then these wires go over and they connect to a circuit breaker panel in your house. So if you've ever looked at a circuit breaker, you'll see that there are generally 2 rows of the circuit breakers. And if you look behind those rows, there's 3 metal bars. There's 1 bar over here, there's a bar in the middle, and there's a bar over here. And these bars are connected to the 3 wires that are coming from the transformer. So you have 1 bar there, 1 bar there, and 1 bar connected to that wire. Okay? So these bars on the outside are called the hot wires. And the bar in the middle is called neutral. So what happens is that most appliances in your house, including the light bulbs in your ceiling, your vacuum cleaner, your hair dryer, you name it. Most of them use the voltage between the hot and the neutral. So that would be 120 volts. So they use that much voltage. So these little circuit breakers that are connected right in here are allowing the electricity to flow from this hot wire through your wiring in your walls, through your vacuum cleaner, and then back to the neutral wire. Okay, so those are the circuit breakers that are hooked up to all of your wall outlets, and they're providing 120 volts. But there are some larger appliances, like you mentioned, like washers, dryers, dishwashers, stoves, ovens, that need higher voltage. 200. So what they do is they use 240 volts. So they use the voltage, the full voltage between these outer bars. Okay? So they use all 240 volts of electricity. So those have to go to special outlets in your wall and they use thicker wire, higher gauge wire in the walls so that that wire can handle that much electricity. And it's the full 240 volts from the outside pairs of bars. So, yeah. Questions about that? Yeah.
Did you say there was a voltage for the neutral?
The neutral is halfway between these. So that's often tied to earth ground. So normally there's a wire that goes from there into the earth somewhere. Sometimes it's attached to a water pipe or something like that, but it's usually attached actually into a spike that goes into the earth. So that's a little bit about circuit breakers. So anybody know why we use circuit breakers? I mean,
For protection.
yeah, they protect us, exactly. What do they protect us from? Right, getting shocked. And what else?
Power surges.
Yeah, power surges. And why is it bad if we had a power surge? Yeah, the appliances. And also, if an appliance started to malfunction and there was a short circuit, say, and that allowed the electricity to flow straight from the hot to the neutral wire, what would happen is that the circuit breaker would, basically what the circuit breaker does is that it looks for a certain amount of current. Most of them are rated for 15 amps. So it'll allow up to 15 amps to go through there, and then if anything more than 15 amps goes through, it will shut off. Okay? So if an appliance malfunctions and allows electricity to flow straight from hot to neutral with very little resistance, that could allow a lot of current to go through there, and that would trip the breaker. What would happen if the breaker didn't trip, if we didn't have a breaker there? And
The wire.
yes, exactly. The wire in the house would start to heat up. So the wires in your walls are all rated for a certain amount of current. Basically, the bigger the wire is, the more current it can handle. So most wire in most houses is rated for 15 amps. That means that it can handle 15 amps continuously and doesn't get too hot. But if it had 20 amps or 25 amps or 30 amps going through there, it would actually start to heat up. And it could melt the insulation on the wire, it could cause sparking, and it could actually heat up so badly that it could either itself catch on fire or light other pieces of the wall or the studs on fire. So that's one of the main reasons that we don't want to have too much current flowing through those wires, because the wires themselves can heat up and start fires. So that's why we need to have the circuit breakers there. Okay? Now, if you've worked in, or if you've been in a kitchen or a bathroom, you've probably seen these special outlets that have these little buttons in the middle, right? That say, so you've got the two little outlets here, and then you've got these buttons in the middle that say test and reset. Anybody know what that type of outlet is called? Yes, ground fault circuit interrupter, or GFCI. Exactly. So these types of outlets provide extra protection where people are most likely to get shocked, basically around water. So that's why they're essential in kitchens and bathrooms. So basically, the way that these work is that you have the electric wires coming in. One side of the outlet is hot and the other side is neutral. And there's a little sensor inside of this box that goes around these wires and measures the current going in and coming out of the outlet through these wires. And this sensor is always checking to make sure that the same amount of current that's coming in is going out again. Okay? If the amount of current going in matches the amount of current coming out, then the outlet knows that everything is working correctly, right? The current is going in through the in wire, through the hot wire, it's going through your appliance, and then it's going back out through the neutral wire. What might be happening if you had more current coming in through the hot wire than you had going out through the neutral wire? What might cause something like that? What's that?
Is it going to turn on by itself?
Yeah, they would cause the switch to turn off by itself, but what sort of situation would allow more current to come in than is going out?
Short?
Yeah, short. Basically, that electricity has to go have another path to go that is not through the neutral wire. Basically, it means that electricity is going through you, going down to ground. Okay, so that would be a very bad situation, of course, and so this outlet is always making sure that the amount of electricity going out matches the electricity going in, so that it knows that it's not finding another path through you to ground. And if it is finding a different path, it shuts everything off. Okay?
What are they, GFCI?
Yeah, GFCI, ground fault circuit interrupter. And these have the buttons in the middle say test and reset. So it's a good idea to test these out in your house. You can test it by plugging in a little light, making sure that the light turns on, and then pushing the test button. When you push the test button, the light should turn off. And then you can hit reset and it should turn back on. If you hit test and it doesn't go off, that means that the outlet is not functioning properly, and you should have someone check it out. Yeah?
How long have these types of outlets been standard in home construction?
I don't know exactly. They've been around for a while, but I couldn't tell you exactly when they came into use.
So they're mainly used in the kitchen and bathroom, right?
Yeah, around wire and around water, and also outside, because it can get wet outside too, of course. So other questions about that? Okay. So we said that the electricity in these big lines that run on power poles, that electricity is at high voltage. That can be in the tens of thousands of volts. And if you've seen those big towers that have those huge power lines going, along I-5 or places like that, that electricity can actually be in the hundreds of thousands of volts. So why would anybody bother to do that? I mean, it's more dangerous. It is difficult to get it up to higher voltages. There's some loss when you use transformers. So why would anybody bother to make the electricity at such high voltages? Well, it comes down to efficiency. And we can actually see this just by using Ohm's law and Watt's law. So let's take a look at this. So imagine that you're over here at your house and you've just come home from a long day and you flip on the light and you're using one of those old incandescent light bulbs. So that light bulb is running at 100 watts in your house. So the power company has to get 100 watts of power from wherever they are over to you. Okay? So let's imagine what would happen if they just ran the power over at 120 volts, right? I mean, that seems like the most logical thing to do. Everybody's using power at 120 volts anyway. Why not just make it at 120 volts and send it down the line like that? So let's see what would happen. The power company creates this electricity, and it has to go down these wires. Okay? Now, when we are doing our labs, we assume that there's no resistance in wires. And that's a pretty good assumption most of the time, because our resistors are up around 1,000 ohms usually. A couple hundred to 1,000 ohms. But wires actually do have some resistance. So let's say, for the sake of argument, that these wires have 10 ohms of resistance. Okay? So if we're doing a lab, our little tiny resistors might have 1 ohm or our little tiny wires might have 1 ohm of resistance. So if we're looking at 1 ohm compared to 1,000 ohm resistor, we can pretty much neglect that 1 ohm resistance. But when you're talking about more power and longer lines, the longer the line is, the more resistance you have. So it is no longer negligible. So let's say that these lines have 10 ohms of resistance, okay? And we have to get 100 watts of power. So we're using this at 120 volts. So we can figure out how much current we're going to be drawing, right? We know that we can use Watt's law to figure out how much current we're going to have. So we can say I equals, or power equals current times voltage. So we can say current equals power divided by voltage, right? So in this case, it's 100 watts divided by 120 volts. So does anybody have a calculator? What does that come out to be?
Like,
0.83 amps. Okay, so we know that we've got 0.83 amps flowing along this wire, and that wire has a resistance of 10 ohms, right? So we can figure out how much power is being lost in this wire, right? We know that there's a form of Watt's law that uses current and resistance. So we say power equals I squared times R. So that is 0.83 amps squared times 10 ohms. So what does that come out to be?
8.3 watts.
It's 0.83 squared first, right?
6.89.
Okay, 6.89 watts. So almost 7 watts, right? So we're using 100 watts in our home, but we're losing 7 watts in transporting it, the electricity from the power plant to our house. So we've got a 7% loss just there. So that's not great. So let's see what happens if we are running at a higher voltage. So instead of running at 120 volts, let's see what would happen if we were running at 10,000 volts. So the power would still be 120 volts, or 100 watts. So then the current is power over voltage. So that comes out to be 100 watts divided by 10,000 volts. So what does that come out to be? So 0.01 amps, or 10 milliamps. So now we have 0.01 watts there, and we can figure out the power lost in the wire again. So we can say power in the wire is I squared times R, so that is 0.01 watts squared times 10. I'm sorry?
Is it amps, not watts?
Yes, thank you. 0.01 amps squared times 10 ohms. So what does that come out to be?
1.001.
So 0.001 watts. Okay, so if we're running at 120 volts, we're losing 7 watts. If we run at 10,000 volts, we lose 0.001 watt. Okay, so running at a higher voltage is much, much more efficient. You lose much less power than you would at lower voltages. So that's why people go to all the trouble to bump up the voltage before they send it over long distances. And the farther they have to send it, the higher the voltage they use. So that's why those really long runs that go along I-5 are using the very, very high voltages in the hundreds of thousands of volts. Okay. So questions about that? Okay. Cool. So we talked a little bit about power distribution. We talked about why we use high voltages. We talked about transformers. So transformers are used all over the place. We talked about using them to go from the voltage at the pole, which is in the tens of thousands of volts, to go down to the 120, 240 level that we have in the home. But these transformers are also used in many other places. So they're used at the power station to go from maybe tens of thousands of volts coming out to 100,000 volts to transport it. And then they're used at other stations along the line. So there are these substations that maybe receive the power from a long way away and they step down the voltage from hundreds of thousands to tens of thousands, and then they put it on these power lines, and then there's another set of transformers that go from the power lines to the house. So transformers are used quite extensively. So we talked about transformers a little bit. We talked about power in the home. We talked about circuit breakers and why they're important, and also GFCIs. So, any questions about that stuff? Yeah.
So are you just telling us that's what's going to be there, or are they going to go over this type of information as well?
So, they are going to talk mostly about the powerhouse itself, and so they're going to show you a gigantic generator, right? So I'm drawing a little picture up here, and I'm hopefully explaining some of the background so you guys know more of the theory of how this works. And then they're going to show you the actual thing and show you where the coils are and show you the big part in the middle. And so hopefully you'll be able to take the theory a little bit and connect it with the actual equipment itself.
Okay, cool.
So they'll talk a little bit about this theory, but they don't have as much time to go into it. They'll spend more time on the actual nuts and bolts of the equipment that's there.
Right. Okay.
Mm-hmm. Yeah. Other questions? Okay. So one more thing about the generator while I'm thinking about it. It creates these three phases, like I said, but this is a simplified diagram. In the actual generator, there are three sets of coils, but they are actually many, many more windings than I showed on the board. Okay, so there's the big permanent magnet in the middle. And then around the outside, there's like one set of coils here, and then the next set of coils here, and then another set over here, and then it repeats. So there's more of the black coils, more of the red ones, and then more of the green ones. And so there's actually many, many, many sets of these windings going all the way around. So the red coils are connected to the other red coils. The black coils are connected to the other black coils. The green ones are connected to the other green ones, and so on. So these sets of windings, there's three sets of windings. It creates three-phase electricity, but there are many coils for each set of windings. Okay. So if there's no other questions, I will take attendance, and then I'll let you go over to the lab. Like I mentioned earlier, there's no formal lab assignment today. It's just a time for you to catch up on any labs that you missed, or do some homework and get some help. Please hand the waivers up to the front, and I'll collect those. You can hold on to the maps, and I will see you at the powerhouse on Thursday.
Yeah. That's needed. All you do is